start by saying that this lecture was arranged by the European Women in Mathematics and the Association of Women in Mathematics and various other groups of women in mathematics. We thank the organizing committee very much for helping to arrange these activities. I'll pass to the introduction of Cathleen now. She was born in Canada from Irish parents. She got her undergraduate degree from the University of Toronto, a master's degree from MIT, and a PhD from New York University in 1951, under the direction of Otto Friedrichs. With Peter Lux, Jürgen Moser, and Louis Nirenberg, and other mathematicians, she was part of the generation that made of Courant the extraordinary institution in pure and applied mathematics that it is today. She's the foremost expert of the analytical theory of mixed-type equations, especially those associated with transonic flow. Her work in these fields includes the proof of non-existence of continuous transonic flows past the profile under small perturbations that admit continuous, small perturbations of geometries that admit continuous solutions. This research helped the development of the shock theory of 2D steady, compressible inviscid flow paths, wind profiles, which was very significant in applications of aircraft designs. Cathleen has also made fundamental contributions in nonlinear hyperbolic equations. In particular, among her extensive contributions are the energy identities that have been the key on many recent developments in the analytical properties of nonlinear wave and scattering theory. She will elaborate more about that. Her academic career started at Courant Institute in 1946 as a research assistant and associate until 1957. She was a research associate at MIT from 1951 to 1952. She has been a faculty member at Courant Institute since 1957, and since 1993, she's a professor emerita, though she has not retired scientifically. She was the director of Courant Institute from 84 to 88. Among her honors and awards, she was a Guggenheim Fellow, a Gibbs and another lecturer of the AMS meetings. She's a member of the National Academy of Science since 1990, Fellow of the Academy of Art and Science since 84, and Fellow of the Royal Society of Canada since 86. She holds 9 honorary doctoral degrees, among them the University of Dublin, TCD, the University of Toronto, and Princeton University. She has been and is still trustee in several institutions and foundations that they include Princeton University, the Alfred P. Sloan Foundation. She has been the president of the AMS from 95 to 97. Just as a side note, I'd like to point out that all these achievements were materialized while she raised, with Herbert Morawetz, 3 daughters and a son, all of them very successful professionals that give them 6 grandchildren. To end on a personal note, I went to work under her direction a few years ago. Cathleen opened my view of applied mathematics with her guidance, clarity, and personal generosity. That was a characteristic all through her scientific career. So, Cathleen.
Thank you very, very much for a very beautiful introduction. It's a very, very great honor for me to give the Emmy Noether lecture here in Berlin at the time of the International Congress of 1998, the last of this century. In my heart, I know that this honor to women in mathematics would have been impossible 40 years ago. To the best of my knowledge, sometimes the ICM gave special attention to small countries, but not to women or certain minorities. But also in my heart is the great hope that say 30 years from now, the need for such a lecture will have evaporated. But now I wish very much to thank my sponsors, the Association for Women in Mathematics and the European Women Mathematicians, and some other sponsors that I have not properly recorded, committees of women of other societies. But I would also like to thank very much the organizers of the Congress for fitting this in to the main part of the program. And now let me turn to the subject of Emmy Noether. Mathematics is the queen of the sciences, and Emmy Noether is the queen of mathematics. I never met her, but she was a good friend of my mentors, Friedrichs and Courant, who spoke to me about her many times. A non-religious Jewish refugee, as you know, from Nazi Germany, she died at the age of 54 in the United States. So she did not live to receive either the position or the accolades that she deserved for her profound work in developing algebra. On the other hand, she did not live to know of the horrors that awaited the Jews of Europe, including many of her old friends, or the terrors of Stalinism, into which disappeared her brother, also a mathematician, or the appalling destruction of the cities of Europe and of many of the friends of her youth. In this talk, I would like to speak of another of her contributions to mathematics other than algebra. This was an application of some invariant theories she was developing, and the application is to partial differential equations. According to what I've heard, she didn't particularly like this piece of work. It followed on some work on invariants that had involved some exceedingly tedious calculations, and she complained about it. But it has generated a number of very important physical applications. So let me begin with her theorem. Suppose we have a system of equations that's derivable from a Lagrangian. I'm not as athletic as the previous speakers, and I intend to use only one of these and not run back and forth. So here we have Noether's theorem, and this is for a Lagrangian system, and to every change of variables that leaves the action of the system, that's the integral over a domain of the Lagrangian. If the action is invariant under the change, then there corresponds a conservation law for the system. So this means there's a one-to-one correspondence between a conservation law and a change of variables. I would like to begin by actually deriving Noether's theorem for a particular case, and that is the case of a trichomy-like equation. An equation, let me see if that works, it does. K of y, uxx plus uyy equals 0, yk positive, which means that this equation changes type. For y negative, it is hyperbolic. For y positive, it's elliptic. And it's in a domain omega, which will, for the time being, remain arbitrary. Now, this equation, in general, has only one invariant change, and that is to shift in x. Tricomy's equation, where k of y is y, has other invariants. Now, the action here, if you've never seen anything like this before, just think of k as 1, and then it's obvious. The action is the integral of kux squared plus uy squared over the domain omega. And of course, its first variation has to be 0, so we compute that. Nothing further than calculus is involved in this. So we compute the first variation, and we arrive at 2kux delta ux plus 2uy delta uy, plus the variation on the boundary. And that gives the term kux squared plus uy squared times delta n, the change in the normal as we change the boundary at ds. Delta n, delta u is the variation in u, and delta n is the variation in the normal. Like other mathematicians before me, it's too hot up here, so I will take off my jacket. And so now, what's this? So now we do the usual thing and we integrate by parts, and of course we get the Tricomi operator in here acting on u times delta u and a piece from the boundary, 2kux dy minus uy dx delta u, plus the piece that we had before. Now, delta u is arbitrary, and therefore, of course, we get back the Tricomi-like equation. But now, from the invariance with respect to x, we get x goes into x plus epsilon, y goes into y, and when we make that shift to leave the u invariant, we have to shift it backwards. So u goes into u of x minus epsilon y. So delta u is minus ux times epsilon, and delta n ds becomes, you have to figure it out, epsilon dy. And so we get then, having thrown away this term, only the boundary term, which is an integral over an arbitrary boundary delta omega. And having done that and rearranged a few terms, we find that the integral around an arbitrary curve of this differential form is 0. Good. That's a conservation law because we could rewrite this as the divergence of something being 0. Now, I made use of this in a paper in 1956. To be honest, I derived it some other way, but Friedrichs told me it was Noether's theorem. So, if you're in 2 dimensions, a conservation law has the very special merit that it defines another function. So we can define the function u by these 2 derivatives, and we get ux is minus 2ux uy, and here's uy. Now, that wouldn't do us any good if it didn't have, it would be interesting, but one would like to make some use of it. And to make use of it, we have to have some properties of the u, the big U. Now, big U has 3 simple properties which we use. The first 2 are derivable just by substitution. The first says that if u is 0 on a curve gamma, then dy du is non-negative if y is positive, or if y is negative and on gamma, dx by dy is greater than or equal to the square root of minus k. That means that this curve gamma in the hyperbolic region has to be flatter than a characteristic. The other property is along any characteristic, dy by du is negative for y negative. And the third property is a little more difficult to prove, and it says that u satisfies a strong maximum principle in y greater than 0. And by strong maximum principle, I mean including Hopf's lemma. So how does that come about? you just form this operator on U, the trichomia-like operator, and you find that you can write it in this way with a nonlinear side on the right. However, it can be interpreted as linear with coefficients alpha and beta of this form. I learned many years ago from Littman and Bayes that a function doesn't know what equation it satisfies, and that you can therefore fool around with this fact. So here one notes that these coefficients are bounded when you write them as nonlinear functions of big U, and they're measurable. And therefore you can apply to this equation a standard elliptic theory as long as you stay away from the axis where k would vanish, and so therefore the strong maximum principle holds. Now this leads you immediately to a uniqueness theorem for boundary value problems. One knows that one gets uniqueness if the homogeneous problem has only the solution U identically 0. So now we have to talk about what our domain omega is going to be and what the boundary conditions should be. So here we take a domain that looks like this. In the elliptic side, it's just some smooth curve with one maximum point. I picked the simplest case, and I call that curve gamma 0. Here there's a Frankel curve. Frankel was another person who went to Russia like Emmy Noether's brother and didn't have such a good long-range fate. On F, we have this condition that it's flatter than a characteristic, and the remainder of the boundary is made up of the characteristic issuing from this point here, endpoint here. So now, where should we prescribe the data? Only on this piece, right? Now there are other theorems for closing the domain and allowing more singular solutions, but this is what we're going to deal with here. So now the theorem is that if d omega is piecewise smooth, in the case I've drawn is, and U satisfies homogeneous data, then, and gradient U is continuous, and K is continuous in the closure, then U is identically 0. Now let's look first at the point D. We're going to use the maximum principle, and it fitted in on this page. That's why it came first. So at D, U sub y is ku sub x squared minus u sub y squared, and u sub x is 0 by the boundary condition, so u sub y is just minus u sub y squared. Now by Hopf, the derivative must be different from 0 if it's a maximum. So therefore, D is not a maximum point, the maximum point for the solution capital U. So let's go back and look at this domain and ask where could U have a maximum point? So I'll just pick a point in omega, right? Then by the maximum principle, it would have to have its maximum somewhere on the boundary of the elliptic region or on the parabolic line. Now along here, by one of those conditions I wrote down, du dy is increasing, so therefore, or non-decreasing, so it would then have to have a maximum at D, not allowed. So therefore, it must have its maximum here, but here you can proceed along a characteristic down towards F, and on that characteristic it's non-decreasing. It's non-decreasing on F by the second condition. I've mixed up the order, but it doesn't matter. So therefore, there's nowhere for it to have its maximum on the boundary if it's continuous, and therefore it has to be identically 0. So that's a proof, and that is the basis for lots of other proofs. and will lead, for example, to many uniqueness theorems for trichomy-like equation. But it does not give you uniqueness for a domain that looks like that. So that's kind of annoying. However, the dimension of the null set for the solutions of the homogeneous problem for this is finite, and therefore that's good enough for many purposes. For example, if you carry this over to the corresponding problem for studying the stability of a smooth transonic flow past a profile, you find that the null set for the homogeneous problem has finite dimensional, and therefore you can show that that problem is ill-posed, and hence that such flows are unstable. So that, in a nutshell, is how one uses Emmy Noether's theorem in order to prove instability for transonic flows. Here then is another sample of a theorem that comes from Emmy Noether's work. So we look at the wave operator, which is such a nice simple operator. Now this operator comes from an action on a Lagrangian, and it's invariant under lots of things, unlike the preceding example where there was only one invariant. Here you can translate, stretch, rotate on a sphere, and you can also, very usefully as it turns out, use a so-called conformal transformation in order to obtain conservation laws. Now, once you have a conservation law for an equation, the equation itself, for example, the wave equation in free space, one knows everything about it. One can do things in many ways. But if you add on something, then you may be able to make use of the conservation part that acts on the wave operator. So let me just go back a bit and take the best known of the conservation laws, derivable from Noether's theorem, and that's the energy identity. So here you see that the conservation law for this is that this divergence expression is 0. Now, it's very hard and a lot of work to derive the conservation laws using Noether's method with the Lagrangian. It's a lot easier to multiply your differential operator by a multiplier and integrate by parts, which, as everybody knows, is a favorite activity at the Courant Institute. So from this equation, if you define the energy as the integral of half ut squared plus gradient u squared at a fixed time, you see that in all of space, it's conserved. It will also be conserved if this term doesn't make a contribution, if you make some other changes, such as putting in an object, right? Put in an object. And put on that object a boundary condition, such as u is 0 or the normal derivative. So therefore you get energy conservation in interesting exterior problems. But now comes the conservation law that we obtain from a conformal transformation. So I would prefer to see this called an inversion transformation, but it got its name before I got my word in. So a conformal transformation takes the variables x, t, and u into big X, big T, and u, and now x is in the space Rm. And I'll define the polar distance absolute x as little r and big X is big R. And now here's the transformation of the variables given by this simple formula and its inverse, which is also has to be very similar. And now the important point is the transformation of the variable little u. So now you make the connection through this formula. And then you find that nabla u, as I like to call it, or D'Alembert u, is some factor, which I omit, times nabla of big U. So if you have a solution nabla u equals 0, it automatically follows that nabla of big U is 0. Now I'll skip over the part of proving that because it's really very easy if you introduce characteristic conic coordinates. And now take the conservation of energy for big U and rewrite it in terms of little u, and you find this. So here's the multiplier which corresponded to big U sub t, and some factors have been taken out, and this can be written as a divergence expression. Now, what does this Q look like? Now, I'd like to use that variable W, which is, did I define it? No. Yes. W is just r to the m minus 1 over 2 times little u, or this thing with the capital U. And then you find that Q has this very nice form. And now, out of that, one is able to prove a lot about the behavior of the wave equation. Of course, for this lecture, I'm leaving out all the boundary terms. But if you had, for example, a solution in the exterior of a star-shaped body, you would find that everything in your integrals are positive, so therefore you can bound things that you couldn't otherwise bound. And the term in Q, so you can imagine this integrated over space, turns out to be bounded in terms of the initial data. And now you see that this is a very nice form, because here you have the angular derivatives of W, which are really the angular derivatives of little u with a weight factor, and it's multiplied by the factor t squared. So therefore, t squared times the L2 integral of the angular variables is bounded in terms of the initial data. And so that means that the L2 integral is decaying like 1 over t squared. And this term tells you the same thing about the derivative outward on the radial direction. And however, of course, something has to give because the energy is conserved, and what gives is the other derivative of W in the other characteristic derivative. However, for R finite and t very large, this also behaves like 1 over t squared. So out of this, you get the decay of solutions of the wave equation in the exterior of star-shaped objects. That's the limitation, that the energy decays like 1 over t squared if you're close to the object. You can also get Sommerfeld's radiation condition out of it. Is that the best one can do? Well, it depends. That's the best you can do in 2 space. In 3 space, wherein with no object you have Huygens principle. In other words, the solution that's of compact support initially leaves a hole inside. Then you get exponential decay. Now that's a very long story, and a lot of work was done on that problem by Lax and Phillips and Melrose and Ralston and Taylor and Maida, and I could go on, Strauss, other people. So that is a big use of our theorem, conservation law. Now, other uses. Well, first of all, that idea of multiplying things by a factor and integrating by parts allows you, without a standard conservation law, to make estimates, again in the exterior of a star-shaped body, of solutions of the reduced wave equation, which are only approximations. In other words, that come ordinarily from geometrical optics. And it was work with Donald Ludwig. And now one can also alter the wave equation by adding a semi-linear term. And here one adds the term f prime of u, and you have to assume that that f of u is positive, and then its contribution to the energy is also positive. Now, of course, that doesn't have a conservation law, and the extra term gives you a derivative with respect to t, which would be fine, but something else here. Now, one needs everything positive to make any use of this, so this term is positive, and this term must be positive. Well, that's fine, but this idea of looking at semi-linear equations goes back to Heisenberg, who proposed as a change, as a nonlinear extra on the Klein-Gordon equation, to add energy terms of the form u to the fourth. This would just give you the Klein-Gordon equation. And for m equals 3, it turns out that this thing has the wrong sign. So that's bad, but one can use the multiplier method and handle that and get decay. In that case, you get the decay very, very slow. Just some integral is finite, and it takes a while to jack that up. But eventually, it led me and Walter Strauss to develop a scattering theory for equations of this type. Now, Strickart, followed by Ginebra and Velo, altered the art of finding decay for semi-linear equations, and they obtained uniform Sobolev space-time estimates for many cases. So multipliers and invariants don't have all the answers. On the other hand, conservation identities that were used originally for decay do provide an unusual and useful handle for some local estimates that are otherwise tough to obtain. They're used by Chatat and Struve in their studies of regularity for semi-linear problems, and also Bourgain and Girard and others have used them. So I'd like to give the flavor of that use for a regularity problem for this equation with Cauchy data of finite energy. Now, the standard energy equation tells you that the integral of u to the p dx is bounded if the initial energy is bounded. And of course, if you're working with weak solutions, you have to do a little work to prove that. And you can get Sobolev estimates for many p's. I won't state exactly which ones, but one sticky case where Sobolev doesn't work is for p equals 2m over m minus 2. So there, in order to be able to get regularity, you have to get just a little bit more than the finiteness of the energy. And the more that is needed is to prove that if you're integrating u to the p dx over a disk, and then set it in a cone and let the cone shrink to 0, then the integral of the energy, or rather of u to the p dx over that disk as it shrinks to the tip of the cone is 0. And out of that, by whatever you want to call it, jacking up or bootstrapping, you can get regularity. So what is the flavor of this method? Now, I decided from watching Helmut Hofer that it might be better to put things on top instead of side by side. So here's the equation, and we apply this multiplier, which comes out of Emmy Noether's theorem for the wave equation, and integrate in a truncated cone. Here's the disk that we're looking at, and we want to push it up into this point. Now, if you try ordinary conservation laws, conservation of energy, then the energy here is the sum of the energy flux across the mantle M plus whatever leaks out at this end. And something could spray out of here because of irregularity. So let's try it with the other kind of identity. And here, with a little notation, C is a truncated cone, D is this disk of radius delta, T equals minus delta, M is the mantle of the cone. And you write down the identity without looking at every term. P tilde is a positive constant. And here is the term of the stuff coming out of the mantle of the cone. And I'm just integrating between here and here. Now, the first merit of this identity is that we can take this disk and push it right up to the origin, because all the integrals involve the factor little t or little r, which is less than t, and times the integral, an integrand of the energy. So that's bounded, and therefore that goes to 0. So we can let t go to 0. And now I have to put in what this Q looks like, and this is the experiment. Is that visible? Any rate, again I write down what my Q is, this expression in W. All I need to note about it is its sign, plus T times U to the P. Now T is negative, so everything here is negative. Now this integral is bounded by the height of the cone, because it also has those factors in it, and plus the energy flux times the energy flux across the M. So now, having let t go to 0, I now use the theorem of Rauch, which tells me that the flux across M goes to 0. So that tells me that the integral of p dc is small o of delta. It's delta times o of little o of 1. So putting it all together, I find that minus delta times the integral I'm interested in plus something negative is equal to delta times little o of 1, divide by delta, and I find the limit as delta goes to 0 of u to the p dx is 0. So that's the second proof, and no more proofs. No more proofs. Now I turn to a quite different topic, which is barely a variation, it's certainly not a variation on the conservation laws, it is a variation on the wave equation. And that is the subject of black holes. I have to be quite frank here. All the world was telling me exactly what I should talk about on this occasion. And someone said black holes. And I thought, it doesn't fit my title, which I gave in months and months ago, and I have forgotten what black holes are. But I went home and I looked in the encyclopedia, which sits in our living room, and I recommend to everybody having an encyclopedia in the living room. It resolves domestic disputes. So I looked up black holes, and there I learned that there are 3 ways in which a star can die. To begin with, most stars are composed of hydrogen. Now let me digress a moment. That most stars are hydrogen was discovered by Cecilia Payne through spectral analysis at Harvard in 1923. But the big shot astronomers around her poo-pooed her results and talked her out of her convictions. So she wrote her thesis up as a maybe, and frankly did not get credit for this enormous discovery until long after the truth had become evident. But back to the death of the stars. Most stars make energy by converting their hydrogen through fusion into helium, and then they proceed down the periodic table through various elements. Now, the first kind of star of the three is small. The process stops, and the star becomes what's called a white dwarf. And small means having a mass of the order of the sun. The second kind of star, which was first postulated by Chandrasekhar, who also went unrecognized for this for many years, is much bigger. It becomes a supernova, and it explodes its mass into the universe. It's about roughly 20 times the size of a star. What happens is it explodes because the pressure beats the gravitational pull. And the third kind of star, which is about 50 solar masses or bigger, turns into iron. And there the fusion process for producing energy stops. If you go further down the periodic table, it would absorb energy, and that's disallowed. So what's going to happen? You're again going to have the pressure of the gas competing with the gravitational pull to implode, but the speeds and the forces are enormous, and they tell us that the phenomenon has to be treated by general relativity. Ah, said I, looking in the encyclopedia, that's where at last the wave operator comes in. So now the bending and twisting of the characteristic of the system gives the gravitational field, and despite the countervailing pressure, a black hole is created. Everything falls into it, and no signals emerge from it. It was so named by John Wheeler, and the fact is that the name alone always excites everybody's fancy, so everyone wants to know about it. Well, that's more or less what the encyclopedia said, but I looked for more, and I moved on to a popular book, Black Holes and Time Warps by Kip Thorne. There are lots of books, so it was just this one I happened to pick on. But I was reminded of Alice in Wonderland. What is the use of a book, thought Alice, without pictures or conversations? Thorne's book had plenty of pictures and conversation. In fact, it's very good reading. But this Alice is a mathematician, and I thought, what is the use of a book in science without equations or formulas? So I turned to more mathematical sources, mostly friends, and so I would particularly want to acknowledge Satya Kitchenasamy, who showed me the equations first, my late father, John L. Singh, who wrote books in relativity, Martin Kruskal, Jalal Shattah, and Demetrius Christodoulou. The problem of the black hole actually goes back to the end of the 18th century, when many believed that light was composed of corpuscles that really had mass. And John Mitchell, he was a rector in the Church of England, and like many other rectors, there are many in science, he preached on Sunday and he did science during the week. He determined the radius of a star from which light cannot leave because the velocity of light, which was known with some accuracy at the time, is less than the escape velocity. Let me remind you that the escape velocity is the velocity that's needed for a vehicle to escape the gravitational field. So stars from which light could not escape were then called dark stars, but of course no observations were made. Now the first relativistic model for a dark star was proposed shortly after Einstein did his first work by Schwarzschild in 1916. He wrote 2 papers while he was serving on the Eastern Front in the German army. And unfortunately, he died of illness very soon after. his model was imperfect and there was a deep underlying problem. But I have to stop there now and go back because this Alice is herself sinning. No formulas, only conversation, not even any pictures. So now let's bring in the equations, and we begin with the metric in space-time. So here is the Einstein metric, ds squared equals g alpha beta dx alpha dx beta. Alpha, beta, and beta run over 4 indices. And I'll also write g alpha beta as a matrix G, and that's a symmetric matrix because of the form. And locally, of course, G can be written in the form that it has for special relativity, with just a diagonal -1 + 1. So Einstein equations are of the form E of G, an operator acting on G, is equal to T. Here comes the wave equation, or the wave operator. E of G leads off with the wave operator on G, followed by 2 nonlinear terms. The first term is quasi-linear. It's linear in the second derivatives of G, and forgive me this rather mixed notation, its coefficients depend on G and the gradient of G. Q2, on the other hand, doesn't depend on the second derivatives, but it's quadratic in the gradient of G, and as a matter of fact, people tell me that that gives you a lot of trouble. Now, the right-hand side of our equation, here T, comes from the gas dynamics of the star, and I'll come back to that later. At least what can be said about this equation is clearly the equations for the 10 coefficients of G, and it separates into the piece on the left, which has to do with the geometry, and the piece of the right, which has to do with the physics. But it's a mess. And in addition to that, there are lots of unknowns in the physics, and which is a fluid, and therefore it's underdetermined. So in addition, there are a number of compatibility conditions. So I shall pass over the famous work of Yvonne Choquet-Brouat, who worked on the initial value problem in the vacuum for those equations, so T is 0, and also the later work of Kleinerman and Christodoulou, which did use the conservation laws I discussed before. And instead, I'm just looking for the black hole. And so let's see what the black hole has to be. First of all, it has to be a hole. That means that all particles have to pass into it eventually. That is, of the particles of the star. And secondly, what does it mean that it's black? It means that no signals can emanate from it. So the first, I'm going to talk only about problems with spherical symmetry, and the first case is the Schwarzschild metric. And here it is. In this metric, T, R, theta, and phi are exactly what you think they should be. And m is the mass of the star, and it's a constant. But when you look at this metric, you immediately see that it has 2 singularities. One is at r equals 0. That's all right. We put it in polar coordinates. We can expect r equals 0. That's where the mass is. There should be something wrong there. However, there's also a singularity at 2m equal to r. And that caused a certain amount of problems. And my father, John L. Singh, in a paper presented to the Royal Irish Academy in 1949, and I have to read this because it's a delicate matter. So following the work of Lemaitre and H.P. Robertson, Singh constructed a change of variables that continued the metric smoothly past r equals 2m, and a full description could then be made of the paths of particles in space-time, not only near r equals 2m, but also near the truly singular point r equals 0. Some years later, a much better change of variables was introduced by Martin Kruskal, gave much better mapping, and that fixed the remaining defects of the Schwarzschild metric. However, it only describes a metric in the exterior of a point source, so that's like reducing all stars to points. So my last stop on the black hole theory, in the last 5 minutes, I'd like to describe the results of the model of Christodoulou, who began his work on this more than 10 years ago. He uses a gas, it's a funny gas to people who work in gas dynamics, but it was suggested by Oppenheimer and has been used by Bethe, and it's the end product of a long, fiery process. So we are again in a spherically symmetric situation, and we write the metric in the following form. Now in this metric, theta and phi are what you would expect them to be. R and omega are the unknowns, and u and v are a set of coordinates, and so this is sort of in characteristic form. And r is a function of u and v, and omega a function of u and v, and those are the things one is trying to find. So Christodoulou introduces as an unknown, instead of omega, the variable m, which represents the mass of the star inside some region. I won't go into the technicalities. And Einstein's equations and the compatibility conditions and the special gas, when they're all stuck together, you end up with the following equations. There's some other simplifying assumption about the scalar field. The first equation is clearly our wave equation in 2 variables, and it's very nonlinear. It has the quadratic terms that we anticipated. It's singular at r equals 0, that's fine, and it also seems to have a singularity at r equals 2m, like the Schwarzschild singularity, but don't forget m is an unknown. So m satisfies what's really an ODE along a characteristic v equals constant. 1 minus 2m over r occurs in a perfectly nice way. R sub u, not so good. And here's another function, phi sub u squared. So if it's true in u, it has to be a similar formula in terms of v. So therefore, it's all very well that you can erase these things, but I have erased too much. Anyway, there should be r squared phi sub v squared in there. So phi has to satisfy a compatibility equation, and here it is. Now, what space should you look for solutions in here? Well, it's natural coming out of gas dynamics, nonlinear gas dynamics, to look for the space of bounded total variation. And then you have to give some boundary conditions, and these should be given on a characteristic manifold because of the nature of these equations. And now out of this, Christodoulou gets his black hole. And where's the picture? Because of the symmetry, or the spherical symmetry, we look at things in the UV space, but of course you have to also think of them in terms of the theta and phi space as well. Now because of that, this is sort of rotationally symmetric, so therefore we're also going to get boundary conditions on the axis where u plus v equals 0. but I won't write them down. They're fairly obvious. So here is the picture of Christodoulou's solution in the space of functions of bounded total variation. Here are the characteristics, v equals constant, and here is a characteristic u equals constant. Well, first of all, where's the black hole? The black hole is where r is equal to 0, and so B, standing for black hole, and B0 constitute the curve on which r equals 0. Now, you will see here that all the characteristics are going into it, right? And that is every characteristic that crosses this curve here. This is the so-called apparent horizon where 1 equals 2r over m, or 2m over r, just as in the Schwarzschild singularity. It's not a genuine singularity of the differential equations, but it does divide the region where the characteristics all enter the black hole, and therefore all particles enter the black hole, because a particle, the world lines of the particle, have to pass between the characteristics. They have a higher slope. H is the last characteristic u equals constant going off to infinity. It's asymptotic to this apparent horizon. So that's, since it's the last characteristic, that means this is truly a black hole. Beyond that, you cannot get any signals. So that is the construction of Christodoulou's black hole in a few words. Now, mathematicians have said a lot more than that about black holes and about solutions in special relativity. And so a lot more could be said. Physicists have explored the interactions of, say, two black holes. There are things called wormholes. I don't know where all that fits in. I'm a novice in this area, to be frank. But I ask myself, where are the conservation laws and where are the invariants? Well, the equations really are invariant under a change of scale. In fact, you can look at those equations and they have many. That's a rather beautiful fact. You might have noticed there don't seem to be many constants in there. That's because one is able to eliminate them. However, the change of scale invariance makes it harder, I'm told, to make estimates, because you can't grab anything and put a number on it and say it's small. They do not seem to have any conservation laws, and I think people think they shouldn't. As to the space of bounded functions of bounded total variation, it's a natural from gas dynamics, 1D time-dependent gas dynamics, but we know it's not right in gas dynamics for higher dimensions, so therefore we need something better. We also know that L2 estimates will be no good for these problems, even for small data. So here is the wave equation. It's in desperate need of new estimates, not only for black holes, but for gas dynamics, because the world's not likely to be spherically symmetric. And that's where I'll leave you. Black holes bring us to the wave operator, but not to its conservation laws. Thank you.
Any question? Well, let's ask the speaker once more for this fantastic lecture.